7.1 Polar Coordinates. So, up until now, the coordinate system that you've worked with is the Cartesian coordinate system or the rectangular coordinate system. And let me grab something, there we go. This right here is the rectangular or Cartesian coordinate system. So this should look very, very familiar. It's the rectangular coordinate system. So you plot a point, and then you have an x and a y value, and this is your x-axis, this is your y-axis, this right here is the origin. The way that we determine where x and y, what x and y are, is based upon their x value here and their y value here. So it's based upon this grid system that we've made. However, this is not the only type of coordinate system that exists. There's also the polar coordinate system, as you might have guessed by the title of this video. And the polar coordinate system looks a little bit like this. Now, technically, let's undo that. Technically, these sit right on top of each other, and they are the same system. It's just they are laid out differently. Let's talk a bit about this. So this is the polar coordinate system. The way that points work in the polar coordinate system, instead of being x comma y, they are r comma theta. R comma theta. So this line right here is the polar axis. Instead of being called the x-axis, it's the polar axis. This point in the middle, that's the origin, as you would expect. But the way that we plot points, instead of having an x and a y value and then going over x, up y, instead we have an r, and that's going to be the distance from the origin, and a theta, which tells me how far to go. So if I plotted a point randomly, right, this distance right here is r, and this angle is theta. So the distance here, if we count the distance from the origin, and it's different, right? These are the labelings for distance right here. So if we go 1, 2, 3, 4, 5, that's 5 for the radius or the r. And then the theta is pi over 3. You can reach all points either way. So both of these systems allow you to reach the same set of points, which is every point in a 2D field. But it's just the representations that are different. So let's talk a little bit about plotting polar coordinates. So when you're plotting polar coordinates, you are going to start by, these kind of can be interchanged. Step 1 and step 2 can kind of go in either order, depending on preference. But one of the steps is drawing theta in standard form. And then the next step is moving out r units and plotting and labeling the point. If r is negative, you move in the opposite direction. So let's plot some points here. I have this point 4 comma 3 pi over 4. I'm going to go ahead and do it in the order that I have the steps here. So I'm going to go to 3 pi over 4. So looking at the angle 3 pi over 4, that's here. And then r is 4, so I'm going out 4 units. So that's 1, 2, 3, 4, right here, if I can remember it. There we go. So this is the point 4 comma 3 pi over 4. Okay. Sometimes we like to draw lines and stuff to show where it is, so you can see this is 3 pi over 4. But I'm just going to leave that dot plotted there. 5 comma 5 pi over 3. So 5 pi over 3 is down here. And then we want to go 5 units out from the origin. So 1, 2, 3, 4, 5. Or you could use this up here and say 5 is here and then go down to here. That would give you your point. So this would be the point 5 comma 5 pi over 3. Let's get a little bit fancier here. So more plotting points. This time we have a negative angle. So negative 7 pi over 4. You have options here. We could make this into a coterminal angle that's an angle that's on here, or you could start at 0 and go backwards 7 pi over 4. Either way works. If you'd like to do a coterminal angle, I think that might be easier. So you would add 2 pi, which is the same as adding 8 pi over 4. And then you get pi over 4. So negative 7 pi over 4 is the same angle as pi over 4. So I'll be going to pi over 4, and then I want to be going out 2 units. So that would be right, oops, nope, that's on pi over 3. That's on 3. There we go. So this is the point 2 comma negative 7 pi over 4. And once again, you could have gone negative 7 pi units. So you could have gone this way, negative 7 pi over 4. But sometimes it's just easier to find that coterminal angle. This guy has a negative radius. So we're going to have to be a little bit careful here. We're going to go to 5 pi over 6 to begin with. That's right here. So I know that this is the line that I would normally go out on if r were positive. If r is negative, you actually end up going the opposite direction, just straight across the circle from it. So you go to 5 pi over 6, but now that r is negative, instead of moving this direction out 1, 2, 3, 4, you move in the backwards direction, directly backwards direction, 1, 2, 3, 4. And that would be your point right here. So this would be negative 4 comma 5 pi over 6. So let's plot 2 more points and then call it good. So this is angle negative pi over 3. Instead of making it a coterminal angle, I'm just going to go ahead and go negative pi over 3. So this is 0. Negative pi over 3 is going to take me right back here. This would be negative pi over 3. Right? So why don't I actually, I'm going to highlight the line. So this would be the forward direction, but our r is negative. So we need to be going directly backwards from there. So instead of going forward 5 units, we're going to be going backwards 5 units. So 1, 2, 3, 4, 5. I think that's right. So this is negative 5 comma negative pi over 3. And then just one more for good measure. So 5 pi over 4 is right here. And we're going to be going the forward direction on this, and it helps to kind of highlight it. We're going to be going the forward direction because our r value is positive. So 1, 2, 3, 4 to right there. This is the point 4 comma 5 pi over 4. So hopefully that makes sense on plotting these points. The negative r values can be a little bit weird, but you're just going in the direct backwards direction. That's the only difference there. So one of the unique things that happens with polar coordinates is that points can have multiple representations. In our rectangular coordinate system, there's only one point that is the point, 1 comma 1. There's one point, it's right there, and there's no other way to represent that point other than 1 comma 1. However, like we experienced in this problem here, having negative 7 pi over 4 as the angle and having pi over 4 as the angle, it's the same point, right? I can go backwards, or I could just find a coterminal angle and go forward and have the same exact point. And there's, in fact, infinite representations of every point in the polar coordinate system. So I kind of wanted to show this. So if we go to 5 pi over 6, that's right here, and we go 2 out, plot this point, it's right here, 5 pi over 6. That's that point, 2 comma 5 pi over 6. 17 pi over 6 is going around the unit circle. So 12 pi over 6 is 2 pi. And then you would have 5 pi over 6 left. So it would be like starting here, going all the way around, and then stopping here on 5 pi over 6. That would be 17 pi over 6. And this would be that point. So same exact point. Same with negative pi over 6. Ooh. Yeah. No. Hold on a sec. There's supposed to be a negative here. Sorry. Otherwise, we would have a much different point. So negative 2 comma negative pi over 6. So negative pi over 6 would be right here. This is negative pi over 6. And that would be the forward direction for negative pi over 6. But because our r is negative here, backwards direction is the one we want to go, 2 units up, bam, in the exact same place as all the other points there. So you can represent any given point infinitely many ways. And one of the problems that you're going to be doing on ALEKS is going to have you doing that. So what I said, we can represent the same point in many ways. The way that you represent points differently, you can add or subtract 2 pi from theta to make coterminal angles. That's one option. The second option is changing the sign on r. So if it's positive, make it negative. If it's negative, make it positive. And then add or subtract pi from theta. Let's do some examples of that. Find 2 representations of the point 6 comma pi over 6 with theta between negative 2 pi and 2 pi. So I'm going to write the equivalent with denominators of 6. So negative 12 pi over 6 comma 12 pi over 6, so that we make sure we don't exceed those bounds. So my first option would be adding or subtracting 2 pi to this angle and just leaving this number alone. If I add 2 pi, if I did pi over 6 plus 2 pi, which would be 12 pi over 6, this would give me 13 pi over 6, which would be outside of my interval. So I can't add 2 pi to this, but I can subtract 2 pi from it. So my first point, I will subtract 2 pi from theta and leave r alone. So pi over 6 minus 12 pi over 6, I get negative 11 pi over 6. So the point that I would have would be the point 6 comma negative 11 pi over 6. For my next one, I have choices on whether I go back to this guy. I think I will start with him again. And now I have to, I've already done the subtracting, I can't add, so I have to go to this one. Changing the sign on r and adding or subtracting pi from theta. So not 2 pi, but pi. I'm just going to add pi instead of subtracting pi, but you could do either. There are many answers here. So I'm going to make r opposite, so it'll be -6. And then I'm doing pi over 6 plus pi is 6 pi over 6. So this would be 7 pi over 6. And those are 2 points that represent the same point. Let's just do one more example. This time with a negative angle and a negative r value. I will begin by rewriting our bounds in the same denominator that we have for our angle. So -6 pi over 3, comma 6 pi over 3. The thing I noticed is if I subtracted 2 pi, I would definitely be outside of these bounds. If you subtracted 2 pi, you'd end up with -7 pi over 3. So we can't subtract here, but I can add 2 pi to this angle and get a nice angle. So my first one, I'm going to add 2 pi to theta, and you don't change the r value when you do this. So negative pi over 3 plus 6 pi over 3 is equal to 5 pi over 3. So my point, I will keep the r value and then 5 pi over 3. Now I have to change the r value. For my second point, I'm going to have to change the r value, so I'm going to make it the opposite sign, and then add or subtract from pi, not 2 pi, but pi from negative pi over 3. So why don't I give both possible answers here? If I took negative pi over 3 and I added pi, so added 3 pi over 3, I would get 2 pi over 3. That would give me the point -4, comma, 2 pi over 3. And that fits within this interval here. My other option, taking negative pi over 3, and subtracting pi, I get -4 pi over 3. Ooh, you know what I did here? You have to change the sign. So 4, it was negative, it's now positive because I have to change the sign. Anyway, -4 pi over 3, so this one will be +4, -4 pi over 3. Just remember, when you're doing the pi, when you're just doing adding or subtracting pi, you're making the sign on the r value opposite. If you aren't changing the sign, that's when you're adding or subtracting 2 pi. So there you go, finding multiple representations of points in the polar coordinate system. So you have a point in the polar coordinate system, and you want to know what it would be in the rectangular coordinate system, because like I said, they do lie on top of each other. You know, you have this regular rectangular system, but then there's circles that lie over it. And so a point in the polar coordinate system is a point in the rectangular coordinate system, and you can find the x and y values for it. The formulas for finding x and y are x is r cosine theta and y is r sine theta. So converting a polar coordinate into a rectangular coordinate, I have the point 5 comma pi over 3. To find the x value, I would do r cosine theta. This is r is equal to 5. Theta is equal to pi over 3. So 5 cosine of pi over 3. Cosine of pi over 3 is going to be 1/2. So I get 5/2 for my x value. So I'm going to do x comma y down here. The formula for finding the y coordinate would be r sine theta. So 5 sine of pi over 3 sine of pi over 3 is root 3 over 2. So 5 root 3 over 2. And that's our answer. That is the xy coordinates of the polar coordinate point 5 comma pi over 3. Now, I think it's a good idea to do a quick logic check and see if it falls within the right coordinates. So if your x and y values are positive, then you are in quadrant 1. The point 5 comma pi over 3 is somewhere here, and then it would be a positive value, so it would end up in quadrant 1 as well. So you know that they both end up in quadrant 1. So that's not telling you that you for sure have the right answer, but it can make you feel pretty good about it. It can definitely catch you if you're wrong, though. Let's go ahead and do another example. I don't have the formulas on this page, but they are x is equal to r cosine theta and y is equal to r sine theta. So, r is equal to 4, theta is equal to negative 7 pi over 4. So, this would be x comma y is what we're looking for. R cosine theta, comma r sine theta. So 4 cosine of negative 7 pi over 4. Comma 4 sine of negative 7 pi over 4. And negative 7 pi over 4, that's almost negative 2 pi, so it's actually going to come all the way up to here. This is negative 7 pi over 4. It's coterminal, negative 7 pi over 4, if you add 2 pi, so if you add 8 pi over 4, it is coterminal with the angle pi over 4. So we are going to hopefully end up with something in quadrant 1. So knowing that these angles are pi over 4, we know that cosine of pi over 4 is root 2 over 2, and sine of pi over 4 is root 2 over 2. So we have 4 times root 2 over 2, comma 4 times root 2 over 2. Simplifying that, you're going to get 2 root 2, comma 2 root 2. Both the x and the y coordinates are positive, which means you're in quadrant 1. So they both end up in quadrant 1, so we can feel pretty good about that answer. One more of these. This one's kind of fun because you actually don't need to use the formulas at all. So looking here, 2 pi would put you all the way around. So 2 pi is just kind of going out this way. Negative for the r value, right? The r value is negative, means that instead of going out in that direction, you are instead coming backwards 2 units. So you have this point right here, which is easy to read in the rectangular coordinate system. That's just negative 2 here because we went backwards. This is the point negative 2 comma 0. You'd get the same answer if you use the formulas, but sometimes it's fun to just, figure it out on your own. Now, normally I would get in how to go the opposite direction, how to go from x and y coordinates into polar coordinates, but I think I'm going to go ahead and skip that. There's a little more intricacies to it. I think I'm going to go ahead and skip that for now. So let's go into converting equations from polar to rectangular. There's going to be 4 formulas you need here. So r cosine theta is equal to x, r sine theta is equal to y, r squared is equal to x squared plus y squared, and theta is equal to tan inverse of y over x. So our goal is going to be, this is an equation in polar coordinates. This is a polar equation because it has r's and thetas in it. And our goal is to make it so that there's no r's and thetas left at the end by using these formulas to replace things. So for instance, r sine theta, that's right there. that's equal to y. So y is equal to negative 6. There are no r's and no thetas left. So y equals negative 6 is that polar equation in rectangular form. Let's go ahead and try another. So I have the formulas over here, and I don't see anything that I can directly replace. I would much rather be seeing cosines right now, so because I have something with cosine, nothing with secant. So I'm going to start by, this is 5 times secant is the same thing as 1 over cosine theta. So r is equal to 5 over cosine theta. And I kind of see something tricky happening here because if I multiply both sides by cosine theta, they'll cancel here, and then this r has a cosine theta, and I can replace it with an x. So I'm going to do that. I'm going to multiply both sides by cosine theta. I now have r cosine theta on the left side. These cosines cancel, equal to 5. This right here is x. So we have x is equal to 5. And that is all our r's and thetas are gone. And so this is a rectangular equation. Now, sometimes the converting gets a little bit weird and sometimes there's some tricks involved. So looking here, kind of an issue because there's nothing here that's r. There's r cosine theta, there's r sine theta, there's r squared, and there's theta, but there's nothing on this list that's just r. So you need to do a trick. And the trick here is if I square both sides, then I have an r squared, which I can replace with x squared plus y squared. So the trick, square both sides. So you have r squared is equal to 4 squared. R squared is equal to 16. But you know that r squared is equal to x squared plus y squared. So instead of r squared, I'll put x squared plus y squared is equal to 16. There are no more r's or thetas left, so that's a rectangular equation and we're done. Now, this one's a little bit different. We have a theta, and we do have something to replace with theta, but we have to do a little bit more work after it's done. So theta is equal to tan inverse of y over x. So I can say tan inverse of y over x is equal to 5 pi over 6. However, while there's no r's or thetas in here, there is still some trig in here, and we kind of want that to go away. To undo tan inverse, we could take tangent of both sides. And that will undo the tangent over here, allowing us to have y over x is equal to tan of 5 pi over 6. And this is a value we can actually find. So thinking about 5 pi over 6, it has, so cosine of 5 pi over 6 is going to be negative root 3 over 2. Sine of 5 pi, I don't know why I'm writing this sideways here, sine of 5 pi over 6 is going to be positive 1/2. That means that tangent of 5 pi over 6 is going to be sine of 5 pi over 6 over cosine of 5 pi over 6. So 1/2 over negative 3/2. Multiplying the top and the bottom of this fraction by 2. And cancel these 2's, cancel those 2's. And it equals 1 over negative root 3. So y over x is equal to 1 over negative root 3. make it a little fancier, multiply both sides by x, just because you can solve it for y very easily. So these x's cancel. You get y equals 1 over negative root 3 x, which is a line actually. So theta equals 5 pi over 6 is a line. And that's its representation in the rectangular coordinate system. All right, last example of polar equation into rectangular equation. We have r equals 2 sine theta for cosine theta. And we have an issue because all of our formulas involve either an r squared or an r sine theta, r cosine theta, and there's no r here. And this isn't an r squared. So the trick here is everybody just needs one more r. Why don't we multiply both sides by r? So multiplying both sides by r, this r would get distributed to both of these terms. So r times r is r squared, and then we have 2r sine theta minus 4r cosine theta. R squared is x squared plus y squared. R sine theta is y. And let's choose a different color here. R cosine theta is x. So x squared plus y squared is equal to 2y minus 4x. This is actually an equation of a circle that's not centered at the origin, but I'm not going to go through the work of putting it into its form. But there's no thetas and there's no r's left, so this is its rectangular form, and we are good. So the last thing from this section is talking about the opposite direction, so taking rectangular equations and turning them into polar equations. So before, we wanted no r's or thetas left. This time, we're going to start with x's and y's, and we want no x's or y's left at the end. Additionally, these are all going to have the instruction to solve for r, so it has to be r equals stuff without r's. So same formulas, really. You don't have to worry about theta, so just these formulas here. X squared plus y squared, that's r squared. And then x is r cosine theta. So we have r squared is equal to r cosine theta. Now, it's tempting to want to divide by r on both sides, and technically you'd get the right answer if you do, but it's improper to divide by r because r could be 0. So really what you should be doing is subtracting the r cosine theta off of both sides so that one side is 0. I can now pull an r out, and I get r minus cosine theta is equal to 0, which gives me two equations. Either r is equal to 0 or r minus cosine theta is equal to 0, which we could add cosine theta to the other side and get r equals cosine theta. Now, you're going to get r equals 0 as an answer a lot. We don't include this answer because this answer is included in here because cosine theta becomes 0 at times. So we don't need to include r equals 0. It's just an irrelevant answer, and this would be the only one that's relevant. So because this one already includes this guy. And there you go. There's no x's or y's left, and we have solved for r. All right, so we're going to convert this equation right here into its polar form, so we don't want any y's or x's left. Let me go quickly grab our formulas and put them on here so we can point to them. All right, so y is equal to r sine theta, so we will replace y with r sine theta equals 5. We've now taken care of getting rid of the y that existed, so there's no y's left, there's no x's left. We just need to solve for r. So to get r by itself, you're simply just going to divide by sine theta on both sides. So the sine thetas here cancel, and you get r equals 5 over sine theta, which if you wanted to be fancier, could be written as r equals 5 cosecant theta, but either of those work. Just two more examples here. For this guy, there's an x and a y. We're just going to use the formulas we were given, and then we're going to try to solve for r. So we have 2, and then instead of x, we have r cosine theta plus 4, and then instead of y, we have r sine theta minus 3 is equal to 0. So I want to move this 3 to the other side so that everything on the left side has an r in it, and I can pull an r out. So 2r cosine theta plus 4r sine theta is equal to 3. I am going to pull an r out on the left-hand side. I'm left with 2 cosine theta plus 4 sine theta equal to 3. Then to get r by itself, I will divide by 2 cosine theta plus 4 sine theta. And I get r is equal to 3 over 2 cosine theta plus 4 sine theta. And that is our final answer on this one. All right, so last problem. This one is going to need a formula I don't have written down here. So remember way back, let's find it. Here, where we had this theta formula, occasionally you need the other version of this, where if you take tangent on both sides, you get tangent theta is equal to y over x. So coming back to our problem, the other formula we would want here is that, let's write it as y over x is equal to tan theta. If you try to go the route of just replacing things, let's just kind of see how that looks. So you would do r sine theta equals r negative r cosine theta. You could add the r cosine theta to the other side, so r sine theta plus r cosine theta equals 0. And then you could pull the r out and you have sine theta plus cosine theta equals 0. But here's the issue. When you go to divide by sine theta plus cosine theta, it's a 0 in the numerator, so you would just get 0. You would just get that r equals 0, which doesn't quite make any sense. That doesn't quite look like a right answer. So we need more tools here. So we know y over x is equal to tangent theta. If I divide both sides by x here, these x's will cancel. I'll have a negative 1 over there, and I'll have y over x is equal to negative 1. Y over x is the same thing as tangent theta. So tangent theta is equal to negative 1. Here, we're actually looking to solve for theta, so that, the reason the r went bad is because we're trying to solve for theta here. So we're going to need to take tan inverse on both sides. We get theta is equal to tan inverse of negative 1. And you can plug this one in your calculator, or you can, remember back to when we talked about inverse trig. But this will give you theta is equal to negative pi over 4. And that would be your answer, solved for theta. So this page back here really should have y over x equals tan theta as one of the formulas. I just thought I would be able to leave it off, but nope, it needs to be there. All right, so that's that for this section. Hope you're having a fantastic day. Thanks for sticking with me to the end of the video, and I will see you in the next one.